Swayam Prabha. Digital India. Educated India.
Hello students, let us continue our discussion on the applications of open system thermodynamics, where we are using the concept of chemical potential and we are trying to understand how we can extend the concept of chemical potential to quantify our understanding of chemical reaction equilibrium. Now, in this regard, today's lecture, we will start by using a thought experiment. And this thought experiment will concern an equilibrium reaction box which is being maintained at a constant temperature and pressure. And within this box, this reaction would happen where 2 moles of nitrogen dioxide in the gas phase will combine to give you 1 mole of N2O4, dinitrogen tetroxide. Now, this is a schematic representation of the reaction setup that we have. And here in this picture, I will highlight what I call as my equilibrium reaction box. In this box, I have an equilibrium chemical reaction equilibrium between NO2 and N2O4, and they are being maintained at a constant temperature T and pressure P. Now, with this reaction box, I have 2 more attachments which are shown here and here. I'm going to call this part as the NO2 side and this part as the N2O4 side. So in this thought experiment, what I will do is I will start with the reacting mixture at equilibrium within this box at a constant temperature and pressure. Then I will pass the reactant NO2 from the left hand side, which is the NO2 side, so that the nitrogen dioxide gas passes through this NO2 permeable membrane and enters the equilibrium reaction box. And I will withdraw the product N2O4 while always keeping the system at equilibrium. Now, I will also make sure that the reactant will always be at its equilibrium partial pressure, PNO2, and it is at this partial pressure that it will be forced through this nitrogen dioxide permeable membrane. Okay, so that means that while forcing, I'm going to use a piston on this side to force the nitrogen dioxide gas through the nitrogen dioxide permeable membrane so that the desired amount of gas can enter the reaction box from the NO2 side. I will also ensure that the product N2O4 passes out at its own equilibrium partial pressure P N2O4. Now, what is it that I'm trying to achieve by doing this kind of experiment? As you understand, if I inject 2 moles of nitrogen dioxide under the defined experimental condition and withdraw on this side 1 mole of N2O4, in that case, the condition of the equilibrium reaction box or this reaction chamber, it remains unchanged from its initial state. Now, my question is, if I have perturbed the system without changing the equilibrium condition of my reaction box, then we can look at this situation a little more closely and decide what has happened while we allowed NO2 to enter the reaction box and N2O4 to be withdrawn from the reaction box, both at their individual partial pressures at the given temperature T and total pressure P. In order to do that, let us assume that I think about an infinitesimal change. And this infinitesimal change of the chemical reaction mixture involves introduction of dN of the NO2 species, dN NO2 moles of nitrogen dioxide in the equilibrium box. And then I would assume that the reaction would proceed by an amount of d xi. So because of this reaction, there will be infinitesimal changes in the number of moles of the reactant as well as the number of moles of the product. And here I find that the dN of NO2, that is going to be minus 2 d xi, and dN of N2O4 is going to be plus d xi as dictated by the balanced stoichiometric equation given here when the reaction proceeds in the forward direction by an amount d xi. Now, the next stage is that whatever moles of N2O4 have been produced as a result of this reaction would be removed in such a way that it is removed at its own partial pressure on the N2O4 side. And here, as a result of this infinitesimal change, I understand what is going to be the net change in Gibbs free energy under the given condition of temperature and pressure. I will have an infinitesimal change in the Gibbs free energy on the N2O4 part, which is this side. I will also have some dG of the equilibrium box, which is concerning the change in Gibbs free energy within the reaction box. And also, I will have some infinitesimal change in the Gibbs free energy of the NO2 part. So, that is the left-hand side of the reaction box. Now, as you understand, if the system is still at equilibrium, then the overall change in Gibbs free energy at this given temperature and pressure must be equal to 0. And therefore, a sum of these three quantities must be equal to 0. But I already understand that within the equilibrium box, there is no change in temperature, there is no change in pressure. And as such, the way the experiment has been designed, there is no change in the composition of the equilibrium mixture. And therefore, I must be having within this equilibrium box, dG is equal to 0. Now, if I think of the consequence of this relationship, then I am forced to conclude that for the experiment that I am describing at present, for the infinitesimal change that I am talking about, I must be having dG associated with the N2O4 part must be adding up to the dG of the NO2 part, and the summation must be equal to 0. Now, if this is the case, the question is, do I know what these individual dG terms are? Of course, by now we know that dG in each of these cases will be mu into dN. Therefore, for the NO2 part, it would be given by mu of NO2 multiplied by the infinitesimal change in the number of moles of NO2 in that part. Because in this particular part, you have lost NO2 molecules. Similarly, on the other side, that is on the N2O4 part, you have gained the N2O4 molecules, and therefore the corresponding change in Gibbs free energy would be mu of N2O4 multiplied by dN of N2O4. So if I put these two equations back in here, what do I get? So this is the equation that I would get if I combine these equations, the earlier equations. So now the equilibrium condition for the entire setup is that the difference between these two quantities multiplied by d xi, that must be equal to 0. But d xi, by the design of my experiment, is a non-zero quantity. Therefore, what do you think is the condition of chemical equilibrium? Under the given setup, the condition of chemical equilibrium turns out to be whatever is there inside the bracket, that must vanish. And therefore, I would say that the chemical potential of N2O4 minus 2 times chemical potential of NO2, that must be equal to 0. So this is the condition of chemical equilibrium that we have been talking about in our earlier lecture. Now, if I look at a finite change, for example, I'm talking about the production of 1 mole of N2O4. Can I have the same kind of argument and find out what is going to be the condition of equilibrium? It is possible, once again, to say that, okay, I am going to disturb the system by introducing delta N NO2 moles of nitrogen dioxide in the equilibrium box at a given temperature and pressure. And then I would expect that the reaction will proceed in the forward direction by a finite amount xi. This would result in a change in the number of NO2 molecules, which would be minus 2 xi, and there will be a consequent change in the N2O4 number of moles of the N2O4 molecules, which would be plus xi. And by the design of my experiment, I'll be removing whatever N2O4 are being generated at its respective partial pressure. So in this case, once again, I can argue that if the system is still in equilibrium, I will have delta G, overall delta G, equal to 0. And the equilibrium box is maintained at a constant temperature, constant pressure, and in spite of introducing the NO2, because of the removal of N2O4 which was generated, the chemical composition inside the equilibrium reaction box has not changed because of this experiment, and therefore, once again, delta G equilibrium box is equal to 0. And therefore, just as before, I understand that the changes in Gibbs free energy at a given temperature and pressure coming from the two additional parts on the two sides of the reaction box must add up to 0. And now, once again, I know that what these individual terms are. I put them back in this relationship, and since I know xi is a non-zero quantity, so once again, the condition of chemical equilibrium turns out to be the condition that we have seen before. And therefore, the point that I would like to emphasize here is that irrespective of whether you are disturbing the equilibrium reaction box at a constant temperature, irrespective of whether it is a finite or an infinitesimal perturbation, the condition of chemical equilibrium depends on the mu values of N2O4 and NO2, and also on the stoichiometric coefficients of these two species in their balanced chemical equation. So moving from here, then I understand that I am able to describe the equilibrium condition in terms of chemical potential. But measurement of exact value of chemical potential is not something that you would do every day in the chemistry lab. And therefore, we understood that when a reaction is proceeding in a given direction, it would be much easier to talk in terms of reaction Gibbs energy, which is defined as the slope of G with respect to the progress of the chemical reaction at a given temperature and pressure. And we have also seen that for the simple case A to B, delta Rg, that is the reaction Gibbs energy, is nothing but mu B minus mu A. So whatever conclusion we can draw from the chemical potentials, they can be translated into using the same information but in terms of the reaction Gibbs energy. We also showed in our previous lecture that delta Rg is a sum of two quantities. And here I have the delta Rg naught, that is the standard reaction Gibbs energy at 1 bar, and RT, L and Q contains the information regarding the composition of the reaction mixture at a given stage. By definition, delta Rg naught is mu B naught minus mu A naught. And now I could say that if I know the Gibbs free energy as a function of the extent of chemical reaction xi, then I will have some idea about the slope delta Rg, and I can connect its value, or as at least its sign, with respect to the direction of spontaneous chemical reaction as well as the condition of chemical reaction equilibrium. So as you see that if you are at a composition where the xi takes up a value like this, you can go up and identify the corresponding point in the G versus xi plot and ask the question, what is the slope of this curve at this point? Here, the slope is negative. If the slope is negative, it says that as the reaction proceeds in the forward direction, that is A converts to B, there is a decrease in the Gibbs free energy. And that is the reason why the slope is negative. This type of reaction condition is known as an exargonic reaction condition because this reaction proceeds with decrease in Gibbs free energy and therefore it can produce work in the surroundings. However, if you are looking at a reaction mixture of A and B at this value of xi, here from the plot of G versus xi, you see that at this stage the slope is positive, which means if I want to carry out the reaction A to B, this will be associated with a net increase in the Gibbs free energy. Therefore, you can always argue that here the reverse reaction, that is the conversion of B into A, will be spontaneous because it is in that direction that the Gibbs free energy decreases. Such reactions are known as endergonic reactions, where the reverse reaction is feasible and the forward reaction is not spontaneous. As you understand, then work needs to be done by the surrounding on the system to carry out this reaction. Now, there is something very important that is coming out from here. Since the slope changes from negative to positive, there must be an intermediate region where the slope becomes equal to 0. And that is associated with the extremum of the plot of G versus xi. And that gives us, obviously, the condition of equilibrium. So the condition of equilibrium we identify as when the reaction Gibbs energy is equal to 0. And that is this point as highlighted in this particular plot. Now, we have already discussed that when the system is in equilibrium and delta Rg equal to 0, then if I put this expression into this equation, this is what we are going to get. So delta Rg0 means this side is 0. That should be equal to delta Rg0 plus RT ln Q, but now the reaction quotient has a value equal to its value when you are having the equilibrium reaction mixture. And immediately I can say that delta Rg0 is equal to minus of RT ln K, where I have used this notation that K is nothing but the value of the reaction quotient Q for the equilibrium mixture. And as I have discussed in my last lecture, this is related to the activity of all the components present in the reaction mixture, each raised to a power nu, which comes from the algebraic stoichiometric equation that we introduced in the last class. Therefore, if your jth component is a product, nu j is a positive quantity. And if Aj is j is a reactant, then nu j is a negative quantity. And Aj is the activity or a quantity related to the concentration of the jth component of the reaction mixture at equilibrium. Now, let me once again take this example and remind you that if I have a homogeneous gas phase reaction where A goes to B and there is a chemical equilibrium between the two species A and B, in that case, I can say that K, that is the equilibrium constant, that is going to be equal to partial pressure of B divided by partial pressure of A measured at equilibrium. Now, with this background in mind, let me remind you that depending on the way you are describing the activity that enters the expression for equilibrium constant, you can have many different types of equilibrium constant depending on the application that you have in mind. For example, this is the general expression in terms of activity coefficients, activity and activity coefficients. I will come back to this when we discuss the electrochemical equilibrium. But for most practical purposes, things are much simpler if you have a gas phase reaction. In that case, you can find out the equilibrium constant for the gaseous reaction in terms of the partial pressures of the components of the reaction mixture. Now, if you have the total pressure in the reaction mixture equal to the standard pressure of 1 bar, then you are going to have the corresponding standard equilibrium constant. It is also possible that you are going to replace the activity by the corresponding concentration, which is Ci in moles per liter. In that case, the equilibrium constant at standard pressure will be called standard concentration equilibrium constant. And in many other cases, especially when you have a gas phase situation, you, instead of using the partial pressures, you can use mole fractions instead, and that will give you mole fraction equilibrium constant. With this, let me once again go back to this example where I have all the information at hand as I have summarized in this particular slide. So this is the reaction that I am following, and I know that in general thermodynamics tells me that I will know if the forward reaction is spontaneous under the given condition or the reverse reaction is spontaneous if I know the sign of delta Rg, where delta Rg is nothing but del G del xi Tp, and this is related to mu B minus mu A. Here B is NO2 and A is N2O4. So please remember that this is just the reverse of the chemical reaction that we were talking about in our thought experiment. In order to keep things simple, I'm going to make an assumption. And the assumption is, in this homogeneous gas phase reaction, my reactant N2O4 and my product NO2, both of them would behave ideally. So now if I look back, I know that the very first step should be writing down this chemical equation as summation over I nu I Ai equal to 0. So in this case, the way I will write it out is summation over NO2 2NO2 minus N2O4, that must be equal to 0. That immediately tells me that for N2O4, nu I is equal to minus 1, and for NO2, nu I is equal to plus 2. And let's say the initial conditions are set such that initially there is 1 mole of N2O4 present and no NO2 was present in the initial reaction mixture. Now you allow the system to react at a given temperature and pressure. And at some stage xi, where the advancement is denoted by xi, what is going to be the mole number for N2O4? That is going to be 1 minus xi. And what is going to be the mole number for NO2? That is going to be 2 xi. Therefore, at this stage, the total mole number is this plus this, which adds up to 1 plus xi. Then you can find out, obviously, the mole fraction for each species and the partial pressures of each species. And when you know that, you can immediately formulate what is going to be the reaction quotient when the reaction has advanced by xi in the forward direction. Now, from standard tables, knowing the Gibbs free energy of formation, standard Gibbs free energy of formation of N2O4 and NO2, you can very easily find out that delta Rg0 for this reaction is going to be 4.77 kilojoules per mole. Then you can immediately say that for an advancement xi of the reaction, delta Rg is 4.77 plus RT, L and Q. Now, when I have this particular situation at hand, that I know the delta Rg0 and I also know what delta Rg is going to be, I can now, for different values of xi, compute the corresponding value of Q, and from delta Rg0, I can find out what K is. And with these informations, I can predict the direction of reaction. So at a given stage, if Q is greater than K, you must say that the reverse reaction must occur to reach equilibrium. What happens if Q is less than K? Then you conclude that the forward reaction must occur to reach equilibrium. So as you see, we have been able to describe the condition of spontaneous change in a chemical reaction and the condition of equilibrium if we know, we have information regarding the concentration of the reaction mixture and the equilibrium constant. Thank you.